Welcome to NPTEL MOOCs course on Computer Vision and Image Processing, Fundamentals and Applications. In my last class, I discussed the concept of background modeling and the concept of the motion estimation. For motion estimation, I discussed one important algorithm, that is optical flow-based motion estimation. Today, I am going to continue the same discussion. So, first I will explain the concept of the object tracking. After this, I will briefly explain the concept of particle filter based object tracking. So, let us see what is object tracking. So, in my last class, I discussed about the concept of the video surveillance system. So, in this block diagram, I have shown the generic framework of a video surveillance system. So, you can see here the input video is available that can be captured by the camera. After this, we have to detect the objects present in an image or the present in the video, and after this we have to do the object classifications, and after this we can do the tracking, the object tracking, and after this the action recognition, and the output is the output video and semantic description. This is a generic framework of a video surveillance system. Last class I discussed about this system, and one problem already I have mentioned, the problem of the shadow. So, we have to remove the shadow. So, if I consider the cast shadow, suppose if I want to do the tracking of an object, the shadow is also moving and the object is also moving. So, we have to remove the shadow. So, based on the motion information, we cannot remove the shadow. So, for this we can consider some approaches. Here I have shown one classical approach in this paper. So, in a shadow region, intensity changes greatly. However, change of chromaticity is negligible. So, based on this condition, we can separate the shadow from the object. So, in this example, you can see the cast shadow is present, and based on this property, that is the intensity variation and also the chromaticity variations, we can remove the shadow. But at present, there are many new techniques for shadow removal. So, this is the classical approach for shadow removal. There are many new techniques of shadow removal. Even in the deep learning framework, we have different methods for shadow removal. So, you can see all these methods. But here I have briefly explained the concept of shadow removal. After this, the next point is the object classification. So, for this we can consider the shape feature for object classification. And here also I am considering a very old paper, but concept is very simple. Based on the shape information, we can classify human and the vehicles. So, for classification of humans and the vehicles, they considered one parameter. That parameter is dispersiveness, and it is based on the perimeters and the area. So, based on this parameter, they classified humans and the vehicle. So, for human, the value of this parameter is 61.8, and if I consider the vehicle, this value is 41.0. The concept is humans are generally smaller than the vehicles but have a more complex shape. So, based on this parameter, we can do the classification of human and the vehicles. And this is also a very old technique. There are many new techniques, like in deep learning also we have many techniques for object classification, or maybe some other feature based techniques we can consider for object classifications. And this is another shape based method, that silhouette information can be considered to detect pedestrians. In this paper, they considered hierarchy template, and based on this template they detect the pedestrians. So, these are the templates, and based on this template they detect the pedestrians. And after this, we have to consider the object tracking. Tracking means finding the correspondence between the frames of a video. So, for this we can consider the model based tracking. Suppose if I want to track humans, then in this case we can consider the model based tracking. So, maybe we can consider a cardboard human model we can consider, and this model can be considered for object tracking, that is for the modeling the human body and to predict the location of human body parts. The human body parts may be the head, torso, hands, legs and the feet. So, this is the cardboard model that is the cardboard human model, and based on this model we can do the object tracking. And also we can consider the feature based tracking. In this paper they considered the color information. Based on the color information they did the object tracking. So in this example what they have considered, they considered the color histogram. So color histogram corresponding to this portion, the head portion, color histogram corresponding to the upper body, and color histogram corresponding to the lower body. Based on the color information they did the tracking. That is the feature based tracking. Here you can see I am showing one example of feature based tracking, the tracking of the ball. So for this there are two popular algorithms. One is the Kalman filter, another one is the particle filter. In case of the Kalman filter, one assumption is the linear assumption. That concept I will explain later on. And also the noise is considered as Gaussian noise. So because of this the Kalman filter cannot track properly. If the motion of the object is very high, then in this case it fails. So the advanced version is the particle filter. It considers nonlinear state equation that I will explain later on. Also the noise is the non-Gaussian noise. So that is why the particle filter can track objects very nicely. If you see in this example, the particle filter can track the objects very nicely as compared to Kalman filter. And I assume that you know the concept of the Kalman filter, because today I am going to explain only the particle filter. So you have to read the concept of the Kalman filter. And one tracking algorithm is the blob matching. So here you can see after background modeling we will be getting the foreground objects, that these are the blobs. So first what we have to do, match blob from the current image with the persons detected in the previous image. So that means just I am matching the blobs of the current image with persons detected in the previous image. So this is the matching. After this I am getting the matching. In this case the matching is 2. Then the match the detected person with the blobs in the current image. So that is nothing but the two-way matching. So by using this two-way matching we can do the tracking. So in the next slide you can see this concept. What is the two-way matching? That is nothing but the blob matching. The blob means that is the foreground objects detected after background modeling. So here you can see I am considering the tracking of these pedestrians, and you can see I am detecting the blobs. These are the blobs after background modeling. So I am getting the foreground objects. So first I have to do the matching. So just I am doing the matching. After this, after matching, I am doing the reverse matching. So suppose this person is detected, and after this again I am doing the reverse matching. That is nothing but the two-way matching. So that is a very simple algorithm. That algorithm is the blob matching algorithm. After this I will consider another algorithm for object tracking, that is the mean shift algorithm. So what is the objective of the mean shift algorithm? An algorithm that iteratively shift a data point to the average of data points in its neighborhood. So for this what we have to consider? We have to consider a search window we have to consider in the initial location. After this we have to compute the mean location in the search window, that we have to compute. After this the center the search window at the mean. So that means we have to reposition of the search window at the new mean, and we have to repeat this until we get the condition of convergence. So this is the concept of the mean shift algorithm. So pictorially this concept I can explain in my next slide. Here I am showing some of the sample points, but here I am considering the distribution of the billiard balls. But let us consider it as the sample points. And this blue circle, it corresponds to the window, that is the region of interest. And corresponding to this region of interest, we can determine the center of mass. So the center of mass corresponding to these sample points within the window, that we can determine. And you can see the mean shift vector, that is the vector from the center of the window and the new centroid, that is the center of mass. So you will be getting the mean shift vector you will be getting, that is the mean shift vector. I have to move the center of the window to the new center of the mass. So that means you can see this is nothing but the center of the window, that is the region of interest. and after this we have determined the center of the mass. After this we have to move the center of the window to the new center of mass. So that means I am moving the center of the window to the center of the mass. After this I am recentering the window, and again I am calculating the center of the mass, and after this again I have to shift the center of the mass to the new mean. So corresponding to this case also we can determine the mean shift vector we can determine, and again we have to shift the center of the mass to the center of the mass, that I am doing the shifting. That is the mean shift vector we can determine, and you can see I am getting the new position of the center of the mass. And finally we have to do this process iteratively, and you can see this is the point of convergence. So I am getting the center of the mass, that is nothing but the center of the window, the search window. So this is the pictorial representation of the mean shift algorithm. So I am explaining briefly what is the mean shift algorithm. So mean shift already I have explained. It is a non-parametric mode seeking algorithm. So I can say it is a non-parametric mode seeking algorithm. So I have to determine the mode seeking algorithm. For a density function, and this mean shift algorithm iteratively shift a data point to the average of data points in its neighborhood, and this concept is very similar to clustering. Suppose let us consider a set S. Set S is considered of n data points. The data points are xi, suppose d-dimensional Euclidean space. And I am considering the vector is x, and suppose let kx is the kernel function. So I am considering the kernel function. This kernel function indicates how much x contributes to the estimation of the mean. Then the sample mean m at x with kernel k can be determined like this. So that means I can determine the sample mean. The sample mean is mx. I can determine with the kernel is k. So already I have defined the kernel I am considering. So sample mean I can determine like this. I is equal to 1 to n, because n number of data points we are considering. So I can determine the mean, that is the sample mean I can determine, and the difference mx minus x. So this difference is called the mean shift. So mean shift algorithm iteratively moves data point to its mean. That concept already I have shown in the previous slide. And each iteration the mean mx is assigned to x. That means at each iteration, that is mx is assigned to x. The algorithm stops when mx is equal to x. So this is the convergence condition. That means the algorithm stops when mx is equal to x. So that means I will be getting the sequence. The sequence x is nothing but mx After this I will be getting M, Mx. So like this I will be getting. So these are nothing but the trajectory of x. So these are nothing but the trajectory of x. And if the sample means are computed at multiple points, then at each iterations, update is done simultaneously to all these points. So this is the basic concept of the mean shift algorithm. For object tracking, we can apply the mean shift algorithm, that is nothing but the kernel based tracking. For this, what we can consider, the appearance of an object can be characterized using histograms, and tracking can be done based on these histograms. But one problem is that is it is hard to specify an explicit 2D parametric motion model to track non-rigid objects. So suppose like a walking person, that is a non-rigid object. So for this, appearances of the non-rigid object can sometimes be modeled with color distributions. So maybe we can consider the color distribution for object tracking. That means the color histogram we can consider for the non-rigid objects like a walking person. So briefly, what are the steps of the mean shift algorithm? The first step is the initialization of the position of a fixed size search window. So this is the first step. The second step is finding of the average position in the search window. Number 2. So finding of the average position in the search window. Number 3, we can consider put the center of the window at the average position estimated in step 2. And finally, repeat step 2 and step 3 until the average position changes less than a threshold. This is the mean shift algorithm. We can do the tracking. So first I have to do the initialization of the position of a fixed size window, that is the search window. After this, the finding of the average position in the search window, and after this put the center of the window at the average position estimated in step number 2. Repeat step number 2 and step number 3 until the average position changes less than a threshold. So this is the brief concept of the mean shift algorithm. So with the mean shift algorithm you can do the tracking. After this, briefly I will explain the concept of the recursive filter, and already I have explained that the particle filter can track objects perfectly as compared to the Kalman filter, and I assume that you know the concept of the Kalman filter in this discussion. So, in case of the recursive filter, the first one is the representation of dynamic systems. So, first the state sequence is a Markov random process, that is the condition. The state sequence is represented by this. So, xk is the state vector at the time k, and I am considering the function, the state transition function. Fx is the state transition function that is considered, and I am considering the process noise of the known distribution, that is uk, and the state only depends on the previous state, that is the concept of first order Markov process. So, here you can see xk depends on xk minus 1, that is the state only depends on the previous state, and in this case what I am considering uk minus 1, that is nothing but the process noise at time instant k minus 1. Here you can see p xk given xk minus 1, that is nothing but the first order Markov process. And similarly we have the observation equations. So, that is represented by zk, fz, xk, comma vk. So, for this what we have considered, zk is the observation at time instant k, and again we are considering the observation function. The observation function is fz, so it should be fz, that is the observation function, and vk is the observation noise with known distribution. So, I am considering the observation noise vk, and in this case I am considering the process noise uk, that is the process noise, and I am considering the observation noise with known distribution. And the form of density depends on these two functions, one is fx, another one is fz, and we have the densities, one is the process noise uk and another one is the observation noise. That is the representation of a dynamic system. So, what are the meaning of the densities? The first one is the probability of x given z1, that is the posterior density. What is the probability that object is at the location xk for all possible locations xk if the history of the measurement is z1 colon k. So, this is the definition of the posterior density. And another one is the prior density. What is the prior density? Probability of xk given x minus 1. That is the motion model. Where will be the object be at the time instant k given that it was previously at xk minus 1. That is nothing but the first order Markov process. So, that is the prior information. Also, we have the likelihood information, that is the class conditional density, that is the likelihood of making the observation zk given that the object is at the location xk. So, that is the likelihood. And what is the tracking? What is the definition of the tracking in this case? The tracking the state of a system as it evolves over time, and we have sequentially arriving observations, that means the noisy observations are available. So, from these observations we have to do the estimation of the states, that is nothing but the tracking. So, we want to know the best possible estimate of the hidden variables. So, we have the observations and the noisy observations, and from these observations we have to predict the state, that is the tracking the state of a system as it evolves over time. So, that is the meaning of the tracking. And in case of the recursive filtering, the filtering is the problem of sequentially estimating the states, that means the parameters or the hidden variables of a system as a set of observation became available online. So, that means we have the observations, and from these observations we have to estimate the states of a system. That is, the filtering is a problem of sequentially estimating the states, that is nothing but the parameters or the hidden variables of a system, and based on the observations. So, recursive filter, that is the sequential update of previous estimate. But if I consider the batch processing, computation with all the data in one step. So, that is the difference between the recursive filter and the batch processing. that is in case of the recursive filter, that is not only faster but allows online processing of data, rapid adaptation to changing signal characteristics. So in case of the recursive filter, there are two steps. One is the prediction step, that means we have to do the prediction. So from p x k minus 1 an observation is available, we have to determine the probability xk. So from the given observation we have to determine the probability of xk, that is the current state we have to determine from the previous state. The previous state is xk minus 1. And after this, that means what is the prediction? The predict next state pdf from the current estimate, that is the prediction. After this we have to do the updation, that is the update step. So update the prediction using sequentially arriving new measurements, because we have the measurements, we have the observations. So from these observations we have to update the prediction based on sequentially arriving new measurements. So that means we have two steps, one is the prediction step, another one is the update step. So that is the concept of the Bayesian filtering. The objective is to estimate unknown state xk based on a sequence of observations. The observations are zk, so we have the observations, and we have to find the posterior distributions. So we have to find the posterior distribution. That is the objective of the Bayesian approach. So this concept I have shown pictorially here. So you can see, first I am doing the updation, after this we are propagating, again we are updating based on the observations. The observations are z0, z1, z2 like this. So we are just predicting, and after this again we are updating. We are doing the prediction, and after this again we are updating. That is nothing but updating and the propagating, updating and the propagating. So this is the concept of the Bayesian estimation, that is the recursive filter. And in case of the Kalman filter, we have considered the Gaussian noise process and the linear state space model. So if you see this function, the function is fx, another function is the fz. So that is the linear function that is considered in the Kalman filter. But you can see, in case of the Kalman filter, we consider this the linear function of the last state, and Gaussian noise signal we have considered. And the sensory model is known linear function of state, and the Gaussian noise signal we have considered. And this posterior density is also Gaussian. So these are the assumptions of the Kalman filter. Practically these assumptions are not true. So if I want to track an object, suppose which moves very quickly, then these assumptions generally fails. So that is why the Kalman filter cannot track objects properly. That is the problem of the Kalman filter. So that is why we may consider the particle filter. In particle filter, these functions, this function we consider as nonlinear functions, and the noise we can consider as the non-Gaussian noise. So what is particle filter? In particle filter, unknown state vector is available. So x 0 to t, so all the states are available, x0, x1, xt, all these states are available. We have the observation vector z from 1 to t, and we have to find the posterior distribution. So this distribution we have to determine. That is the problem of the tracking. So that means we have to determine this one, that is the filtering distribution we have to determine from the observation. And prior information is given, that is the prior on the state distribution it is given, the sensor model is given, and we have considered the Markovian state space model that we have considered. So this information is available. Now in case of the particle filter, that posterior density is represented by a set of random particles. So we have to consider random particles to represent the posterior density. If I consider large number of particles, suppose n number of particles equivalent to functional description of the PDF. The PDF is the posterior density. And if I consider n tends to infinity, then this particle filter approaches is the optimal Bayesian estimate. That means it approaches optimal Bayesian estimate. So here you can see I am showing the concept of the particle filter, sample base PDF representation. The PDF is represented by random particles. Regions of high density, we are considering many particles, and also the large weight of particles. And here you can see uneven partitioning. So region of high density we are considering, suppose, so more number of particles we are considering, and here you can see corresponding to this we are considering the large weight. So the weight of this particle is large as compared to this, and this is nothing but the discrete approximation of continuous PDF. So what are the steps of the particle filter? That is the sequential importance sampling we have to consider. So first the particle filtering steps for m is equal to 1 to m. So first we have to define the particles, that is the particle generation. After this we have to compute the weights for the particle. So for each and every particles we have to assign the weights, and also we have to normalize the weights. The weight normalization we have to do by using this equation. And finally we have to estimate the states, that is the estimate computation. So we are estimating the states. So these are the steps, that is the first one is the particle generation. After this we have to assign the weights for the particles, and after this weight normalization, estimate computations. But what is the problem? After few iterations, all but one particle will have negligible weight. That is called the weight degeneration problem. So for this we have to do the resampling. The solution is the resampling. Replicate particles in proportion to their weights, done again by random sampling, and we have to eliminate particles with small importance weight. That means the particle having the negligible weight, that we have to neglect. That is called the importance sampling. So this concept I am going to explain in my next slide. So here you can see this PDF is approximated by the n number of random particles, and you can see I am assigning the weights corresponding to all these particles. These are the weights. You can see this particle has the maximum weight as compared to this particle, and after this we have to propagate these particles. So move the particles, and before the moving the particles we have to do the resampling of the particles, move the particles, and after this we have to do the prediction. And this is the step of the particle filter algorithm. So that means the PDF is approximated by random particles, and also we have to determine the importance weight we have to determine, and after this we have to do the resampling, and after this we have to propagate the particles, that is the move the particles, and after this the prediction of the xt given the measurement. The measurement is z 1 to t minus 1. So based on this we have to do the prediction. And the concept of the resampling, because after some iterations some of the particles will have negligible weight, that we have to eliminate. So here this concept, the concept of the resampling I am showing here. The PDF is approximated by the particles, the random particles, and the associated weights. So these are the weights, and you can see some of the particles have negligible weights, that we can neglect, and after this we can propagate the particles, that means we can move the particles to the next step, and like this you can see in the next step this particle has negligible weight, that we can eliminate, and like this we can move the particles into the next step in the next iteration. Like this we have to do, and we can also predict the states based on the measurements. So this is the concept of the resampling. So briefly I can say this is the particle filter algorithm. First, randomly I have to initialize the particle, that is nothing but the discrete approximation of continuous PDF, that is the PDF, that is the posterior PDF is approximated by random particles. So that is the particle generations, and after particle generation we have to compute the weights of the particles by using that mathematics. After this we have to normalize the weights. After this we have to resample the particles. So we are getting observations, and based on these observations we have to do the tracking. So we have to do the tracking like this. In this case, from the normalized weight we can estimate the output, that output estimate we can do, but the problem is that after some iterations some of the particles will have negligible weight. So that is why resampling is important. So we are doing the resampling, and after this we are doing the particle generation, weight computation, normalized weights, and after this we can output the estimates, and based on the observation we have to do the tracking. So this is the particle filter algorithm. So briefly I have explained the concept of the particle filter, but I think you have to study the research papers to understand the concept of the particle filter in more detail. So here you can see I am showing the tracking of this person, tracking of this. So based on the particle filters, so first one is the prediction, again after this the measurement, after this the resampling. The resampling concept already I have explained, because we have to neglect the particles having negligible weights, that we have to neglect, and after this we have to do the iterations. So based on this we can do the tracking. So this is one example of the tracking, and this is also another example of the tracking. You can see the tracking, and I can show some of the videos of tracking. So we have developed this algorithm, the particle filter based algorithm for object tracking. So you can see these videos. So we have done this particle filter based tracking, and also we have proposed some the background modeling algorithms. So based on this we have done the tracking. So in this case you can see the background is cluttered background, and also the illumination is also changing. In this case also we are doing the tracking, and in this case you can see in one case the person is occluded by the car, by the vehicles, and in this case also we are successful in doing the tracking. So this is also another good example of the tracking, and here you can see we are finding the trajectory of the movements. So this person is moving and we are finding the trajectory. So you can apply the particle filter algorithm for object tracking, and again I am showing this example of the particle filter based tracking. And sometimes you can see that one person is occluded by another person, and in this case also the particle filter can track. Particle filter can handle the partial occlusion, and these are some tracking results. In some of the cases you can see, in this case, in this frame, these persons are occluded by this vehicle, and partially these persons are visible. Even then also we can do the tracking. So the tracking is successful with the help of the particle filter. That means the particle filter can handle partial occlusion. And these are some tracking results. Already I have shown the video, and also briefly I will explain the concept of the multiple camera based tracking. So what are the advantages of multiple camera based object tracking? So one important advantage is that the field of view can be increased. So in this case you can see I am considering one camera C1, another camera is C2. So this person is visible by both the cameras. So this camera can see this person and this camera can see this person, and you can see the field of view increases because of the use of two cameras. In case of the multiple cameras, we have to find the correspondence between two cameras or multiple cameras. In this example you can see I am considering the camera 1 and the camera 2, and I am finding some transformation to find the correspondence between these two cameras. So this is the world plane, and suppose if I want to track the object, so we have to find the correspondence between camera 1 and the camera 2. So for this we have to consider some transformation. So some like maybe some the projective transformation we can consider. And another advantage is that because the field of view will increase, that means the occlusion can be handled in a multiple camera based system. In case of the single camera based object tracking system, the problem is the occlusion, but in case of the multiple camera based system, since the field of view increases, so the problem of the occlusion can be partially eliminated. In this example you can see one person is completely occluded by a tree, and this is one view of the camera and this is another view of the camera. Maybe in the another view the person is visible. So that is why the occlusion problem can be partially resolved by considering multiple camera based systems. And already I have explained we have to find the correspondence between two cameras or the multiple cameras. Here you can see, and this is the camera 1 view and this is the camera 2 view, and I am finding the correspondence between these two cameras, the corresponding pixel positions. So based on this corresponding pixel positions we can do the tracking. So I am not explaining in detail how to find the correspondence between these two cameras, but concept is that so we have to find the correspondence between all these cameras in a multiple camera based tracking system. And here I have shown the one tracking example, the multiple camera based. Here I am considering two cameras, camera 1 and camera 2, and I am finding the correspondence between these two cameras, and you can see just I am also doing the tracking, and also I am finding the trajectory of the motion. So all these persons are tracked. So this is one view and this is another view of the camera, and again I am showing the results of multiple camera based object tracking, and these are some examples of multiple camera based object tracking. Tracking single person who is partially occluded by a moving car using two cameras, because already I have explained, if I use multiple cameras, the problem of occlusion can be partially eliminated because the field of view increases because of the use of the multiple camera. In this class, I briefly explained the concept of object tracking and the concept of particle filter based object tracking. For more detail, you have to see the research paper on object tracking and also the research paper on particle filter based object tracking. There are many new techniques of object tracking. The deep learning techniques are also used for object tracking in a single camera based system and also the multiple camera based system. So for this, you have to see the recent research papers. Let me stop here today. Thank you.